Hey everybody, in this video I want to talk about the different properties that different types of substances have. The very first substance that we are going to start with are going to be the metals, and I'm referring to the metallic elements in this case. Metals have luster or shine. Metals are also malleable, which means that they are able to be deformed. They are ductile, which means that they are able to be pulled into wires, as in this image where you see metals that are both shiny, they are malleable, and you could pull them into wires like the ones in the picture. They are good conductors of heat and electricity at almost any temperature. Metals are insoluble in almost everything except mercury, because if you've ever heard like dissolves like, and since mercury is a metal, then mercury can dissolve other metals. And when mercury and metal alloy mixtures form, they are called amalgams. Now, all solids are at room temperature except for mercury, which is a liquid. Metals typically have high melting and boiling points. They have high densities because, again, they are mostly solids. And even though mercury is a liquid, it has a pretty high density. Now, metals are usually very hard, except for, mercury, because liquids cannot be hard. And sodium and potassium are not hard as well, because although they are solids, they are soft and can be cut with a knife. Now, metals have variable reactivities. For example, sodium has 1 valence electron, and it has 1 out of the 8 valence electrons that it is supposed to have. And because of this, sodium very easily is able to lose this electron and become Na+. And it wants to do this really badly because sodium is a very reactive substance that wants to become stable and become sodium+. So to showcase its reactivity, it actually explodes when it touches water. So when you put sodium in water, this happens, and depending on how much sodium you put, the explosion can be small or it could be big. Now, another metal like gold, it's generally unreactive because it has a relatively stable electron configuration. Because if you look at the valence electron configuration, it is going to be 6s1, 5d10. That's 11 valence electrons out of the 18 that it wants. So it is true that gold can lose 1 valence electron to become Au+, and have no 6s or 6p valence electrons, but it typically doesn't do that because it has 11 out of 18, and losing or gaining electrons is not very important to it as much as it is important to sodium. Now, metals are also electropositive, which is the opposite of electronegativity. It just means that the atom does not want electrons. So for something like sodium, sodium doesn't want electrons. Instead, it wants to lose electrons. So that's why sodium is very electropositive and not very electronegative, because these two are opposites. Now, metals form cations, like sodium+, and metals are bound together by metallic bonds. Let's now talk about the next substance, non-metal elements. Non-metal elements are typically non-lustrous, and one exception is I2, because iodine displays some metallic properties such as luster, and in this image you can see that I2 is pretty shiny, so it does have luster, even though it's a non-metal. Now, non-metals are mostly brittle, which means that they fall apart easily when put under stress, and this applies to only solids. So for example, these iodine chunks are pretty brittle, and as you can see, there are many tiny little chunks that are falling apart from it, which kind of proves that it is brittle. Now, even though diamonds are hard, diamonds can be brittle because they shatter into many pieces when enough external pressure is put on the diamond, instead of deforming like metals do. So just because something is hard, like diamonds, doesn't mean that it is brittle. Now, nonmetals are typically poor conductors of electricity and heat, and one exception is graphite, which is an allotrope of C, and if you remember, graphite is a covalent network solid, and the fact that it is a covalent network solid might have to do something with its good conductivity, which contrasts with many nonmetals in the subcategory. Now, some nonmetal elements can dissolve in nonpolar liquids, since like dissolves like, and elemental substances are typically nonpolar. So, as an example, I2, iodine, will dissolve in carbon tetrachloride because they are both nonpolar. Now, most nonmetals are solids and gases, with one exception, which is bromine, and bromine is a liquid at room temperature. Now, nonmetals have variable melting and boiling points. For example, O2 has a very low melting point, while C in the form of diamond is a solid and has an extremely high melting / boiling point due to its covalent network. Now, gases have a low density, while solids have a high density, and this applies to almost everything. There are 7 nonmetals that are diatomic molecules in nature, and we've talked about that in a few videos in previous units. Now, there are variable hardnesses because diamond is hard, while something like O2 is not hard because it is a gas. And let's read on. So, the reactivity of nonmetals varies. So, for example, F2, or fluorine gas, is highly reactive due to it wanting to go from sharing electrons to having 8 valence electrons for itself, or in other words, it wants to form fluoride, since fluorine is highly electronegative and would rather take than share electrons. Now, another gas, like N2, is generally unreactive because N is not very electronegative like F is, and because of that, nitrogen gas is generally unreactive. Now, nonmetals are electronegative. They form anions, such as Cl- or F-, and the forces keeping nonmetal elements together are LDF forces and perhaps covalent bonds, and that only applies to the covalent network solids. So without LDF, this iodine would not be able to remain as a solid because there would be no intermolecular forces, and because there's LDF, these solid particles are able to form because the iodine molecules are attracted to each other and kind of pack together to form a solid. So these forces keep these molecules together, and they're the reason we have solids and liquids in the first place. Now, let's take a look at metalloids, or semimetals, and these are also elements as well. Now, our semimetals are going to be boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. And this is just from the staircase on the periodic table. Now, semimetals have both properties of metals and nonmetals. And, for example, semimetals can either be lustrous or non-lustrous. For example, silicon, which is over here, is pretty shiny and has luster, and arsenic has luster as well, but it is covered by tarnish since it reacts easily with the air around it. Now, semimetals can either be brittle or malleable. Now, silicon is brittle, but most of the semimetals are actually malleable. Semimetals conduct electricity and heat under the right conditions, and generally, a high temperature means more conductivity. So you could control the conductivity of semimetals, and that's the reason why they are used in computer chips, since you can regulate how much conductivity the metals have depending on the temperature, and it's really useful in the tech field. Now, they are called semiconductors because they can conduct well depending on the conditions and not all the time like metals can, since metals are always conductive regardless of the temperature. Now, all the metalloids are solids at room temperature. They have variable melting / boiling points, And to demonstrate this, silicon has a covalent network, so it has a very high melting and boiling point, while other metalloids might not have as high of a melting or boiling point. Now, since they are solids, they are generally dense. They have variable hardness, and they can gain or lose electrons during reactions. Now, let's be even more specific and go into the subcategories of metals. So the first one I'm going to talk about are the lanthanides. Lanthanides start with lanthanum, and they are at the bottom of the periodic table. They are silvery metals, they are soft, they have F valence electrons, they tarnish quickly in air, and their cations can sometimes be colorful. Now, actinides are another subcategory of metals. They are all radioactive substances. They easily tarnish or react with air. They are fairly soft metals, and because they are radioactive substances, they are used in nuclear reactors. Now we have the transition metals. The transition metals are typically hard, typically very dense. They typically form colored ions and compounds due to having unfilled d-electron sublevels. For example, copper 2 is going to be blue. Now, one exception to this rule is zinc, because zinc, specifically zinc 2+'s d-electrons are completely filled, and because of that, the ion for zinc, Zn2+, is not colorful. Now, the reason why these ions are colorful is because the d-electrons can jump up and down energy levels, and jumping up and down energy levels releases light, and this light is what we perceive, and sometimes this light can be colorful, which is why sometimes these transition metal ions can be colorful. Now, transition metals are also used as catalysts because some of these transition metals, such as platinum, or maybe a compound like manganese dioxide, are able to speed up reactions, which is why they are called catalyst. And let's write that word, catalyst. Now let's talk about the alkali metals, which is group 1. Alkali metals such as sodium and potassium are relatively soft. They have a silvery color. They are highly reactive because they explode upon contact with water, and their reactivity increases down the group since the first ionization energy decreases down a group. And because of that, elements that are down the group, such as francium, can lose an electron very easily. Now we have the alkaline earth metals. They are pretty similar to alkali metals, except that they are less reactive than alkali metals, but they are still relatively reactive, and they have a silvery color. So now let's move on to the next type of compound. We are going to look at nonpolar covalent compounds. Refer to video 7.3 to get more information on the bonding behind covalent molecules such as I2. Now, these nonpolar covalent molecules are typically non-lustrous, except for I2, as we just saw before. They are typically soft and brittle. They are typically poor electrical and thermal conductors. They have low melting and boiling points most of the time, and one exception is I2, because I2 has very powerful London dispersion forces since it has a large electron cloud. Now, these nonpolar covalent molecules are typically gases at room temperature, and the exceptions are bromine and iodine and more. Now, like dissolves like again, and this causes nonpolar covalent molecules to dissolve well in nonpolar liquids such as carbon tetrachloride, oil, and etc. And the forces that keep nonpolar covalent molecules next to each other and keep them as solids, such as in this picture, are LDF. In this picture, I2 is dissolved in carbon tetrachloride, another nonpolar molecule, and in the end, you get a solution that looks magenta. In this image, we have dry ice, which is carbon dioxide in its solid form, and dry ice sublimes at room temperature. And as you can see, the solid is turning into a gas in the picture. Pretty neat, right? Now let's look at polar covalent molecules. Remember to refer to 7.3 for more information about the bonding. Now, these molecules are non-lustrous typically. They are typically soft and brittle. They are typically poor electrical and thermal conductors. And if you notice, I keep on saying typically, and this is because these properties only apply most of the time, but not 100% of the time. So you can never be 100% sure about anything. Now, polar covalent molecules typically have low melting and boiling points, but these are typically higher than those of non-polar molecules. These are typically solids, liquids, or gases at room temperature. These are dissolved well in polar liquids such as water, alcohols, which have that OH group, which is a very polar group, and etc. And again, like dissolves like. Now, what are keeping polar covalent molecules together? Well, LDF, dipole-dipole forces, and sometimes H bonding. Now let's look at this cool diagram that I drew. So in these two cases, a person is bringing a charged rod and they are either positively or negatively charged, and in both cases the water will move toward the rod, and this is because water is polar. And notice how the partially negative end of the water molecule is attracted to the positively charged rod, and in this picture the partially positively charged end of water, which is the hydrogen, is attracted to the negatively charged rod. So if you put a charged rod near a thin line of water, it will move towards it. Now let's take a look at the properties of ionic compounds, also known as salts. So they have crystalline structures, they are solids at room temperature, they have high melting and boiling points, they are hard and brittle, they do not conduct electricity as a solid because there are no free-moving ions, but they do conduct electricity when dissolved in water or any other solvent, and this is because in a solvent they become electrolytes. Now these solids are good insulators because they don't conduct heat or electricity as a solid. Now, solubility depends on the salt, but many salts are soluble in water and other polar substances like alcohols, and the forces keeping the ions together are called ionic bonds. In this picture, we have copper 2 sulfate, and notice how it has a transition metal in the salt, and that's why it's colored blue, for example. And in this picture, we have table salt, which is sodium chloride. In this picture, we have baking soda, which is sodium bicarbonate. Now we have to talk about covalent network solids. They have very high melting and boiling points. I should say very because they have one of the highest melting and boiling points out of all the solids. They are poor conductors except for graphite. They are typically hard. They are mostly crystalline, such as silicon dioxide's crystalline form, which is quartz. And diamonds, which are allotropes of carbon, are also crystalline. Now, they do not dissolve in water or many solvents at all. They are brittle, so for example, silicon dioxide can be glass, which is the amorphous form of silicon dioxide, and we all know that glass is pretty brittle because it cracks when you drop it. Now, diamonds are also brittle. Now, most covalent network solids are hard. Now, let's talk about amorphous solids. Amorphous solids, again, have no repeating unit or orderly crystal structure. Glass, for example, is the amorphous form of silicon dioxide, and many plastics, as well as wax, are also amorphous solids. Now, amorphous solids do not have a definite melting point since the bonds do not break all at once at one temperature. Instead, there is a melting point range, and that is why when wax melts, you don't get a liquid immediately. Instead, you get a soft, mushy solid. So in this example, glass is amorphous, so when you melt it, it becomes molten because it does not become a liquid immediately. It instead becomes this malleable substance, And glass blowers use this property to shape glass into sculptures and other amazing things, such as vases, for example. So that's pretty cool. And amorphous solids have no symmetry, and they have variable melting points and boiling points, or instead of melting points, I should say melting ranges. Now let's talk about our final type of solid that we are going to go over. These are crystalline solids. Crystalline solids have repeating units unlike amorphous solids, and these repeating units are called unit cells. They have orderly crystal structures, and quartz, which is the crystalline form of silicon dioxide, has a crystalline structure. Salts have a crystalline structure, and some molecular solids, like ice, have crystalline structures. So in this image over here, you can see that the water molecules form a crystal, and the crystal is held together by hydrogen bonding. Now, crystalline solids typically melt and boil at more exact points than amorphous solids do. They are symmetrical, and they have unit cells, and some of these unit cells include simple cubic, face-centered cubic, and body-centered cubic, and we went over these three simple unit cells in video 7.5. Now, another word for cubic is isometric, and we also have other forms of unit cells. We have something called the rhombohedral unit cell. We also have hexagonal unit cells, which look like this. We have triclinic, tetragonal, monoclinic, and orthorhombic. I don't know if I pronounced those right, but monoclinic looks like this, and this is different from simple cubic because, as you can see, that's not a 90-degree angle. That's like angle beta, and that's not 90 degrees. So the shape kind of slants down a little bit, and that's why it's not considered cubic, because in a cube, all the angles are going to be 90 degrees, such as here, maybe here, and even here. So yeah. Now, crystalline solids have variable melting and boiling points. So that's all for this video. Have a wonderful day.